Last last week we had, I think it was Stephen asked this about the where the Curiosity and Perseverance were with respect to each other,
Yes.
and I found this map that shows everything except it was done before the Chinese rover. So, but I know about where it is. So uh, they were still using the old name there, Mars 2020. We call it Perseverance now. Is up here, and here's Curiosity over here. Now, actually, notice Curiosity is really close to that InSight lander, which is interesting. I didn't realize they were that close. Now, that doesn't mean, I mean, that's still hundreds of miles, but much closer than I realized. Some of these things you may not, like Mars 2 and Mars 6, were rovers that crashed, and never, or landers really, that crashed. We didn't hear anything about. The Chinese rover is up here close to the location of Viking 2. So somewhere in this area. So fairly far away from Perseverance or Curiosity for that matter. So we do have some news from the Perseverance mission today, and that is that the helicopter flew again, and actually flew yesterday. And we know this because I pointed out several times that if you go to the NASA's website for this mission, you can get the latest pictures, and there are classifications of pictures from the various cameras on the rover, but there's also a classification for the helicopter cameras. And this morning, there is a series of pictures posted from yesterday taken by the helicopter's cameras. And these are the navigation cameras that we talked about last week, the black and white ones. And so when the helicopter is flying, what you see is its shadow. And that's exactly what we see here. And we're actually going to go through that whole series to show kind of what the flight went like. NASA had announced, I think it was over the weekend sometime, that this flight was going to take place. And they had originally said it might take place Sunday, but it in fact didn't take place till yesterday. We know that because you remember last week we learned that those pictures the helicopter takes are time stamped. And so we can check the timestamps on these pictures, and they're from yesterday. So this is when the flight actually happened. For the flight that had all the problems, they had done a flight plan and announced it before, and it was fairly complex. They gave you a lot of details. In this case, the flight plan for this flight really did not. It basically said, well, the helicopter is going to take off. It's going to fly about 350 feet south, and it's going to land. So it didn't give the kind of detail that we've seen before. And it may be that that's strictly all there was. I assume we'll find out sometime later this week more about exactly what it did. But one thing about this is that from the direction it flew, it was flying over the surface where it had not flown before. And so it couldn't depend on previous pictures it had taken to guide it. So it's flying, this mission was flown strictly making use of the satellite images from the satellites that orbit Mars in order to figure out what it should do to follow this course and how to find the landing site. So as I said, there's no official release from NASA yet about the flight. However, there is a news story out, which I found, and it didn't have very much detail, but apparently somebody on the NASA project team contacted the reporter and said, yeah, the flight went fine, no problems like the last time. And they also indicated that on this flight that the helicopter climbed to a new record altitude. And we're going to look at these pictures now, and you can kind of get the reason why we might think that's correct. So that's the first picture. That's the same one with the in the beginning. So that shows the shadow of the helicopter just after it took off. And then each succeeding one, you'll see a couple things. The shadow of the helicopter gets smaller, which means that the helicopter itself is getting higher. So that's how we can kind of make a guess about the altitude. The other thing we can do, let's go back for 1 second. Yeah, from here it's so low, you can't really make out any particular features on the ground, except there's this little dark blob down here that's going to come more into view here. Now the helicopter's flown like toward the bottom of the picture, so the dark blob is now up here. And notice this little bright patch has appeared. So those are some kind of features on the ground, and we can kind of figure out the direction the helicopter flew for the way those things change. So if we go to the next image, it's gotten a little below the white blob. Also, it's gotten higher, which we can tell from two things. The shadow of the helicopter itself is smaller, and this white patch up here is smaller than it did in the previous picture. So if we keep going, it's smaller still here. Some new features have appeared over here on the ground. That's the original white blob, and now some new white blobs are appearing here. And it's obviously higher. And here it's higher still because the shadow is much, much smaller. And again, we see the other features, and now some new features are coming in down here. I think that is, no, one more. This is the last one, and it's gotten even smaller. And again, we see these features that's sort of flying over. Now, if you were, as some people I mentioned last week, there are a lot of people who are just totally enthralled with this. I'm fairly enthralled myself, but not to the level of some people. Some people will have saved because you can download these pictures to your local computer. Some people will have saved every picture, and they'll compare the shadow size and figure out exactly from that how much higher the helicopter must have been on this trip than on previous ones. So in that way, that's why somebody's able to say, well, it went higher than it's gone before. One question that occurs to me is, why did it go higher? You know, we mentioned these flights serve two purposes. One is to locate features on the ground that might look like they might be places that the rover might want to go in order to, because there might be some interesting geological property there. And the other is to locate any potential hazards that the rover might encounter on its way. Well, for both those purposes, you want to really be as low as you can. So why on this particular trip did they go higher? I don't know at all. But being me, I am going to advance a theory about this. It may be that they're trying to find out, you know, how high they can actually get the helicopter, and why would they want to do that? Well, it may be that there are certain places where they're going to need the helicopter to fly to a greater height than it has before. Now, one such possibility, and again, this is absolutely pure speculation by me. We have seen before pictures of the rim of the crater where the rover landed, and we've seen in particular the area where that river delta from the river 3.5 billion years ago came into the crater and built up that delta. And we mentioned that geologists are really want to know about that because that means it's built up layer after layer of sediment, and you can find out all kinds of interesting things from that. And from the pictures that we looked at earlier, we know that that delta where it comes into the crater is up much higher than the area where the rover actually landed. So it may be that they want eventually they'll want the helicopter to fly over that area and get as close to the surface as it can there. But that would mean that it would be, that would, unless they waited until the rover got to the up there, that would mean the helicopter would have to climb fairly high in order to get good pictures of that area. So that's just a guess by me, and I say it's total speculation. But perhaps when the NASA releases the detailed information about this flight, they will let us know about that. So we'll just have to wait and see how good a guesser I am. Okay, does anyone have any questions so far? Okay, so let's go on to our next story. This is also about NASA, but it's much further story from much further away than the one about the Mars rover. NASA's released some new images of the center of the Milky Way. So this picture shows us the central area of the Milky Way, and somewhere in here would be located that enormous black hole that we know is in the center. Now, this picture is actually a composite from two different kinds of images. It's made from X-ray images, and the stuff you see that's bright white and also the stuff that's kind of purplish come from the X-ray images, and the rest of it's radio images, and the orange colored stuff is from radio images. So what they've done is taken those two images and merged them together to produce the one we see here. Now, the X-ray images were taken by this NASA X-ray telescope, which it orbits the Earth, called Chandra, and that's a picture of what the telescope looks like. And then the radio images are made by this radio telescope array in South Africa, which is called Meerkat, and we've actually talked about it before. It's got a whole bunch, I think there's 64, if I remember correctly, radio dishes like this, and then they're all hooked in together to produce radio images. And they actually took 370 separate total images. So I don't know how many were X-ray and how many were radio, but 370 separate images, and combined them to make that initial image. Now, if we go back to here, it looks like in most cases the bright white and the purplish stuff is located away from the orangey stuff, so that the radio emitting regions are separated from the X-ray emitting region. But there is one example where that's not true, and we have this is just a single combination of a single radio image with a single X-ray image. The X-ray here being in blue, and this time the radio is in pink. And as you can see, there's some overlap here. The pink being part of this thin blue column that we see. So you can't, of course, tell from this image, but that thin blue column is actually about 20 light years long. So it's really enormous. And it's perpendicular to the plane of the galaxy. So it kind of, if we picture the galaxy as a spiral, it sort of sticks up from the spiral. And the reason it has that very narrow shape, astronomers think, is because there are some extremely strong magnetic fields at the center of the galaxy, which they think are related to the supermassive black hole, and they kind of confine the gas that's causing the X-rays and the radio emissions here. Now, the gas there, this is kind of like a thin blue cloud of gas, and they think that came from a supernova explosion when a star blew up and blasted part of its envelope out into space, and it got into the magnetic field and got pulled into this column. And it's because that the supernova explosion ionizes some of that gas, and so you get charged particles moving, and that's what causes the radio emissions. We've discussed before that when you have moving electrons, there's a tendency for them to radiate energy at radio frequencies. Now, the X-rays, they think, are probably due to something else, and that is that this magnetic field, which occurs in the center of the galaxy, is subject to all kinds of stresses and strains because of the gravity of the black hole. And sometimes the magnetic field lines actually get snapped because of the space being warped by the gravity of the black hole, and then they reconnect. And when they do, they emit enormous amounts of energy, and that's responsible for the X-rays. So that's how we come to get both X-rays and radio being emitted from this one part of the area that was in our original picture. Okay, any questions about this story before we go on? Okay, now we're going to change fields here. Our next story, the headline says, promising new treatments found for advanced prostate cancer. I'm sure it's just a coincidence, but this story came out this week when I happened to make my annual visit to the urologist, which I imagine most of the men my age probably do that, though maybe not everybody. But you know, and actually now it's more like it used to be. They would run tests on me and so on. And fortunately for me, although I have often showed this elevated prostate-specific antigen, and several times they've actually done biopsies to check, but I've never actually shown any sign of cancer. but a lot of men my age have to do this, and that's because that prostate cancer is pretty common. I don't know actual statistics, but I personally know a number of people who have it. So I know just from personal experience that it's a fairly common cancer. Fortunately, uh, it can usually be controlled as long as it stays in the prostate gland. Then either by doing surgery or by doing radiation, you can keep it under control, so that it's not really that big an issue. You know, nobody wants to have cancer, but controlled prostate cancer is one that doesn't really cause you that much problem. Where you run into trouble is if that tumor spreads outside the prostate, and then it's much more difficult to treat. Uh, so the story is about a new treatment, essentially for this type of cancer, for prostate cancer that spread into other parts of the body. And there was a trial done on a new treatment, and they just announced some of the results last week. And I wanted to talk a little bit about it because the actual treatment is kind of interesting, and it relates back to something that we talked about when we were discussing our topics in biology. Now, the drug that was used in this trial is a type of drug called a radiopharmaceutical. When we talked about the radiation treatment for contained prostate cancer, there are two different versions that are commonly used. One is external radiation, where they just focus X-rays on the prostate area. They have an X-ray machine. They focus the X-rays in on the prostate gland and treat it with X-rays, so that tends to control the cancer. The other technique is to implant a radioactive pellet inside the body adjacent to the prostate gland. And in that way, you can use, you're using a much lower level of radiation. And it's pretty well as successful a method of treating contained prostate cancer as the external radiation is. So how do these radiopharmaceuticals work, this new treatment? Well, a radiopharmaceutical is a combination of two different molecules. One of them is a molecule which can bind to a specific protein, which is called a prostate-specific membrane antigen. It's abbreviated PSMA, a little different from PSA. And prostate-specific membrane antigens usually exist in prostate tumors, but not in normal prostate cells. So that's a way to distinguish a normal prostate cell from a cancerous one. Is this specific protein present? So the radiopharmaceutical has a molecule which can bind to the PSMA. And then the other molecule in the radiopharmaceutical is a radioactive molecule. So what happens is they administer this drug intravenously, just hook you up to an IV and pump in this radiopharmaceutical, and it travels through the bloodstream. And if it happens to encounter a prostate cancer cell, then it will bond, because it has that one molecule that binds to the PSMA protein, then it will bind onto the prostate cancer cell. And when I said earlier, this is something we talked about earlier when we were talking about biology, this kind of binding, remember, takes place because this molecule here is exactly shaped to match a receptor in the PSMA protein. So it will fit like the old key going into a lock. And that's how the radiopharmaceutical gets bound to the PSMA protein. And once it's bound, then the radioactive molecule delivers its dose of radiation, and that kills the cancer cell. And the big advantage of this is that since you're actually going to bind this radiopharmaceutical onto the cancer cell, you can the radioactive molecule can give a very, very low dose of radiation because it's going to be right there at the cancer cell. It's not like you are beaming radiation from outside the body and hoping to hit a cancer cell with it. You're now actually attached directly to the cancer cell. So a low level of radiation will then kill that cancer cell. And the good part of that is that as this radiopharmaceutical circulates through your bloodstream, it's not doing damage to healthy tissues because it's very low level radiation, and it won't bind to anything except the cancer cell. Otherwise, it will simply flow through the bloodstream, and eventually it'll get removed by the kidneys and excreted from the body. And so if it never actually finds a prostate cancer cell, then it will leave your body. And so there's very little chance that it will have any undesired bad side effects. So the trial they did involved 800 men, and that all of them had advanced prostate cancer that was no longer responding to other treatments. So what that means is basically they were terminal, because if you can't treat this advanced prostate cancer outside the prostate, then eventually it'll be fatal. So what happened is that the fatality rate was reduced by 38% in the group of people that received this drug. And so when you consider the fact that otherwise they were almost certainly not going to survive, then being able to save 38% of them, that's significant, especially if you're one of those 38%. Out of the survivors, 60% of them showed a decrease in the rate of progression of the cancer. So not only did they survive, but their cancer was no longer increasing at the rate it was before. And actually, some of them turned out to be cancer-free, which basically says that the radiopharmaceutical found and killed all the cancer cells. And the study director said that if they used this treatment on people who are in a less advanced stage of the prostate cancer, then they think it'll be even more effective because those people will have less cancer cells, and so there's better hope that they can eliminate them completely. The other hope is that there are other types of advanced cancer that can be treated in the same way. The only thing that's required for this treatment to work is that the cancer cells have some kind of protein, such as the prostate cancer cells have, so that you can find a molecule that will bind to it. And if you can do that, then this same treatment should work, because once you bind the radiopharmaceutical, then the radioactive molecule will be able to use its radiation to kill the cancer cells. So it's really a fairly promising treatment for a cancer that's quite serious, and it has also the possibility of maybe being used in other types of cancer as well. Okay, does anyone have a question about that? Okay, so let's go on to our next story. And our headline here says, and we're back in astronomy again, high energy gamma ray emission detected by telescope in Africa. We talked about gamma ray emissions being detected by a telescope last week, but that one was in China. And this one's in Africa. So the first thing that attracted me to this story, I'll be very, very honest here, this gamma ray telescope in Africa, I had no idea that this telescope was there. Now, in our story last week of the telescope in China, it's only been in operation since 2019. So it's a very recent telescope, but I knew about it. I had read about it previously, that it was under construction and going to be used. This telescope has been around since roughly 2002. And somehow I had not heard about it. So it just caught me really by surprise that this telescope was even there and that it's doing work like this. It's called the High Energy Stereoscopic System Telescope, which is an acronym is HESS. It's located in Namibia, which is in the southwest Africa. And here's a map of where Namibia is. And the other thing that I didn't realize, I knew that there are quite high mountains in East Africa, in Kenya and Tanzania and Uganda, and even, I guess, some in Central African Republic. I did not realize that there are some high, not so high, but significantly high mountains in this part of Africa, in the southwest part. But indeed there are. And here is the telescope, and we see, again, it's actually an array, in this case of 5 gamma ray detectors. So this report came out last week, and the way that this detection was done by the Hess telescope is that first the gamma rays were detected by some space telescopes. The NASA telescopes called Fermi and Swift. And they were able to determine where the gamma rays were coming from. And so they immediately pointed the Hess telescope at this area of the sky where the gamma rays were coming from. And they were able to follow gamma ray emissions from the source for 3 days. And that's pretty amazing because normally all you catch is just a flash of gamma rays, and then you have to try to deduce whatever you can from that. So what kind of event was it that they're detecting? And because we know that the gamma rays lasted for such a long time, astronomers think there's only one possible event that could be responsible for that. And that would be if a really, really large star exploded in a core collapse supernova, and then afterwards the core of the star then collapsed to form a black hole. And our current understanding of astronomical processes says that's the only thing that would be able to produce gamma rays that would last for such a long period of time. Now, it turns out that this particular supernova was actually closer to the Earth than most. It was only about 1 billion light years away, whereas typically when we detect this kind of thing, they're coming from about 20 billion light years away. So that meant that because it was so much closer, that the astronomers were able to get a much more complete picture of the frequencies of the gamma rays. Well, I should stop for a minute. Even though we talked about them last week, let's say again, gamma rays are the most energetic form of electromagnetic radiation. And since the energy of electromagnetic radiation is proportional to frequency, that means that they have the highest frequency of any form of electromagnetic radiation. But there are a whole range of frequencies that are considered gamma rays. And in this case, they were able to detect a number of different frequencies in this gamma ray event. Now, the reason why they were able to detect so many frequencies is because the source was so close. If you have your typical source, like one that's like 20 billion light years away, then there are going to be a couple of things that are going to happen that are going to cut down on the how much of the gamma rays you'll be able to detect. One is, like any other electromagnetic radiation, as it travels through space towards us, it's expanding. It's like, if you think of it like as starting at a flash back at the source, like a light bulb turned on, then that radiation as it comes towards us is making a spherical wave and spreading out and spreading out. And so if it comes from 20 billion light years away, then that means it's really spread out quite a bit compared to if it comes from only a billion light years away. And so because it's spread out so much, then we're not able, the part that we actually see with our telescope is a much smaller part of the total wave. And so we don't get nearly as much radiation to judge by. Then the other thing that happens is just the fact that the gamma rays travel for 20 billion years. That gives them time to get absorbed by some kind of intervening matter. If the gamma ray are on their way here and they happen to encounter anything, an electron, a proton, whatever, then they'll get absorbed. And when they get re-radiated, they go off in a random direction. There's no guarantee that we'll still see them. Some of the absorbed gamma rays will get re-radiated in a direction that takes them totally away from us and we'll never see them. So it's only because this particular event happened so close that the astronomers were able to detect so much of the shape of the gamma ray spectrum, that is to determine what frequencies were actually involved. And because they were able to do that, the thing we haven't mentioned up to now is that the NASA satellites, in addition to the gamma rays, also detected X-rays coming from this event. Now, X-rays are the next lowest energy electromagnetic wave below gamma rays. And so they also detected a lot of X-rays, and they were in the same way they were able to figure out a spectrum of saying, well, we got some of this frequency, some of that frequency, and so on. And so they're able to essentially make a graph that shows the frequency of the radiation versus how much the quantity that they detected. And it turned out that when they compared the graph from the gamma rays to the graph from the X-rays, that they had a very similar shape. And that was a complete surprise to them, because the theory that astronomers have developed for explaining supernova explosions says that gamma rays and X-rays are caused by completely different properties of the explosion, and there's no reason why they should have the same kind of frequency distribution. The X-rays are thought to be produced by the shock wave of a supernova. When the star explodes, a large bunch of the material is just blasted out into space, and it produces this big shock wave, something like you would get from a conventional explosion. And the energy in that blast is so powerful that it rips electrons away from the atoms. And the electrons are carried along by the shock wave, and they're accelerated as they go through the magnetic field of the black hole that's being created, and that causes causes X-rays to be produced, and so the X-rays that are detected pretty follow the theory that astronomers have, but their theory says you can't get gamma rays that way, because the amount of energy produced is not strong enough to accelerate the electrons to the point where they have to go faster to produce gamma rays, because gamma rays have higher energy. So according to the current theory we have, the way you get gamma rays is this, that you start producing these X-rays, and some of them get absorbed by electrons that didn't emit any X-rays themselves yet, and that pumps the energy of these electrons up even higher, and now their energy is high enough that they can emit gamma rays. But it's a very random process that one of these X-rays would happen to get absorbed by an electron, and so by that theory, you would just expect the emitted gamma rays to have just sort of random frequencies, and certainly not have the same kind of frequency distribution that the X-rays do. So this is a mystery, basically what astronomers have to do now is go back to the drawing board and come up with a different theory of supernova explosion to explain where the gamma rays are coming from. Because what this observation says is that the theory they've used up to now really doesn't work. It really won't explain why we see gamma rays. So if you're an astronomer, it sort of depends. If you were heavily invested in the existing theory and you thought, wow, that's great, and suddenly find it doesn't work, then you're probably unhappy. But other astronomers are happy just because it means, wow, there's something we don't understand out here, and we can go to work and see if we can come up with a new theory that will explain it. So this kind of observation will make some astronomers unhappy and others happy. But that's the way it is with most things that we come across in science. Whenever we see something new, some people are happy because there's a new thing that they need to explain, and people who see the new thing and don't have an explanation for it, but are unhappy because they thought they knew what was going on and now they don't anymore. Okay, does anyone have a question about this story?
Bill, this is Taffy. I have a question, and maybe I'm confusing different concepts, but I believe we learned that the age of the universe is 30 13 something billion years old, right?
Right.
So I'm a little confused
Okay.
by this
Yeah,
being
I see where the
20
question comes
billion
from.
light
Yeah,
years.
right. Yeah.
Um,
The thing that you have to take into consideration there is the fact that the universe is expanding,
yes, okay.
and it's I always feel weird when I say this because it just sounds like it's nonsense, but the expansion rate of the universe is not governed by the speed of light. It can expand as fast as it wants to expand. And so even though we think that the universe has only been around for 13.6 billion years, in that time it's been expanding. So we actually, I don't know if I've ever said this or not, but most astronomers now, if you ask them how big is the universe, will tell you it's 40 billion light years. And that's due to the expansion. So yeah, I don't blame you. That's an excellent question because it's very counterintuitive, and it's kind of mind-boggling. But that's why we could see gamma rays coming from 20 billion light years away, and that's because the universe has expanded as it's aged, and so now it's bigger than we might think it would be.
Okay, thanks. That
Okay.
kind of makes some sense, yes.
Right. Yeah. Well, it's as I say, it's one of the more puzzling things about the universe, but almost all astronomers think that's correct.
Okay.
Any other questions? Okay. Well, I'd like to thank everybody for coming today. Hopefully by next week we'll have some details on this helicopter flight that we can pass along, and we'll have some other stories. But also, it turns out, and I'm not positive yet, but I think it's going to be this way. You're going to get a chance to hear me twice next Wednesday, because before we do our science news, I'm going to do a special program. And the topic of special program is going to be 3D printing, which is something that I've always wanted to know more about. So I thought, well, if I try to explain to people how 3D printing works, I'll have to learn more about it. So I'm in the process of doing that right now. And so next week, if it goes the way I think it's scheduled, 1 o'clock next week, we'll have a program on 3D printers and how they work and what you can do with them. And then we'll have our regular science news at 2:30. So I hope you'll all join me for that. And I will see you next week.
Thank you, Bill.
Thanks, Bill.
Thanks, Bill. Very
Thanks.
interesting.
Thank you, Bill. You just answered the question that I raised my hand for to ask.
Oh, okay, great. I'm glad I did.
Thanks a lot.